Welcome to the course of Converters for Electric Vehicles and Photovoltaics. This is the third module of introduction section. In this module, the module name is Converter for Electric Vehicles. That module is divided into two classes. In the first class, I will be discussing about the converters requirement of electric vehicle, what are the converters are there inside the electric vehicle, and their voltage rating and the power rating. And in the next class, I will be discussing about the characteristics of those converters, and there are different topological aspects. What are the different topologies that is available for the electric vehicle? This is the block diagram or overall block diagram of electric vehicle converters. As the name suggests, the electric vehicle, it is fully run by the electrical power. Now battery is the main power source of the electric vehicle. Generally, lead acid battery, it can also deliver that amount of power, but lead acid battery size is very high and the weight is also quite larger. Therefore, high density battery is required. In current technology, lithium cell battery is quite acceptable in the market because it can provide high density power. The voltage level is also less and it can provide sufficient amount of current to drive the electric vehicle motor. Now, the battery can be connected in series to improve the voltage level, but connecting battery in series creates the charge imbalance problem. Therefore, battery cells are connected in parallel, and that essentially make the system low voltage and high current type. So, battery which is used inside the electric vehicle is essentially low voltage and high current type. Now, as the name suggests, the drive will be totally dependent on the electric vehicle battery. So, therefore, battery needs to be charged periodically if they are based on the SOC level. Now, the charging of the electric vehicle has different aspect of the electric vehicle system, and discharging of the battery, that means driving the electric vehicle, there is another aspect of the total system. Now, this aspect can be divided into two broad categories. If if I talk about the charging infrastructure or charging system for the electric vehicle battery, that can be categorized into two ways. One is either wired system or wireless system. That can be electric vehicle battery can be charged through wireline charger or wired charger, or it can be charged through wireless system. In current advancement, wireless charging is quite popular because we do not need to use any kind of charging infrastructure. We cannot use any kind of onboard charger system. Only receiving coil is required. So receiving coil and interfacing converter can charge the battery. That is about wireless system. And for the wired system, there are two type of procedure we can charge the battery. One is onboard charger, that if some countries or some states, if they do not have any kind of sufficient charging infrastructure, so for that case onboard chargers are useful. Now, onboard chargers are essentially of AC to DC type. That means AC voltage 230-volt single phase or 400-volt three-phase system will be converted to DC system. And DC voltage, I already told, the battery is essentially low voltage type, so therefore it has to be maintained 48-volt voltage at the output so that the converter can charge the battery. That is about the onboard charger. That means the charger is already placed inside the electric vehicle, and outside we can directly plug in 230-volt AC or 400-volt three-phase AC, and that can be directly converted to DC system. So essentially, this kind of converter do need some kind of important features that also I will discuss in the consecutive slides. Another thing is the offline chargers. If the charging infrastructure is available, then that electric vehicle battery can directly be charged from the offline charger. So there, in that case, there is no requirement of onboard chargers. Now, the offline charger is also similar type, either AC to DC. It converts AC to DC and required voltage. And if there is a requirement of fast charging, so that also the DC output DC will be regulated to the 48. Only difference is that if DC fast charging is used, the voltage level is quite larger, which is ranging from 500 to 600. Or else, if slow charging is recommended, or it is this slow charging infrastructure is available, in that condition 230-volt AC or 400-volt three-phase systems are used. And again, in that condition 48-volt need to be maintained as well. So this is about the charging converters. Another converter, as I already mentioned, the battery voltage is essentially of low voltage type, so that cannot be interfaced with the DC link or inverter voltage, inverter to drive the motor. that 48 volt or very low voltage needs to be converted to sufficient high amount of voltage around 300 to 400 volt, and after that the inverter can work to drive the electric vehicle motor. Generally permanent magnet synchronous motor or BLDC motors are used for driving the electric vehicle motor. Now the momentary power requirement is also there, because there may be a chances of acceleration or deacceleration. So in the acceleration case, the momentary power cannot be supplied by the lead acid battery, because the response time is quite larger. So to mitigate this issue, there is a supercapacitor is there inside the electric vehicle, which can supply the momentary power requirement. So there is another converter is required, which is the bidirectional DC to DC converter. Why bidirectional? Because that power supercapacitor can give the momentary power requirement to the drive when it is accelerating in nature. When there is a deacceleration, then the stored energy can be directly fed to the supercapacitor, so there is no wastage of power. So for that we need a bidirectional DC to DC converter here. Generally DC link voltage, I already mentioned 300 to 400 volt, because that is the sufficient minimum voltage required to drive the electric vehicle inverter. So inverter converts the DC voltage to sufficient AC voltage, which can run the AC motor, or that is either of BLDC or of permanent synchronous motor type. Another important converters are placed inside the electric vehicle to actually drive the lighting load or music system load is essentially of buck converter type or step down type, which is with the power is coming from the DC bus, and it converts from 380 volt to directly either 12 volt to 24 volt. And there is a multi-port type, because multi-port type is required because there may be a n number of or any number of lighting system, or maybe large number of music systems. So for that there are different kind of output is required. So for that reason multi-port DC to DC converters are required. So in general this is the block diagram. Generally onboard charger, or if onboard chargers are not available, if infrastructure charging infrastructure available, then offline charger. And then for supercapacitor we do need the bidirectional converter, and for taking power from the main battery unit, which is the lithium cell battery, that is a high gain boost converter. And lastly we have multi-port converter for auxiliary power supply, and the inverter to drive the motor. So this is in general the power converter and their requirements inside the EV. Now I will be discussing in details about each section. Let us go to the charging infrastructure. As the name suggests, it has to be AC to DC, because AC system either of single phase or three phase, that AC should be converted to the DC, and that DC should be regulated in such a way that it can give a 48 volt and to charge the battery. Now when normal rectifier circuit is used, let us say there is a rectifier circuit, normal rectifier circuit. So normal rectifier circuit is used, and simply it converts the AC to DC. Let us say for 230 volt AC system it converts to DC, and then there is a DC to DC converter to regulate the DC voltage. So this is your DC to DC converter to regulate the voltage, and directly it can now will give to 48 volt battery to charge. Now in that system what happens, that voltage may be sinusoidal, but current is a kind of distorted in nature. So it injects, this kind of system injects lot of harmonics to the system, or it deteriorates the input power factor. Therefore the charger what is used here, that topology of the rectifier should be revised in such a way that the voltage and current should be unidirectional in nature. That means the power factor should be close to unity, or 0.99 at least. This is the one important requirement if you are using the if the wired charging is being used. Now in the wired charging it may be onboard charging system, then also that this requirement should be fulfilled. Another thing is that if it is offline charger, then also this kind of requirement should be fulfilled. So the topological aspect, it should be converted fast AC to DC, that is the primary objective, and from DC to DC it should be regulating the output voltage, the second requirement. And the third requirement is the power factor should be close to unity for both the applications. Now the charging time of this kind of system is quite slow, because we cannot regulate the current here. So to regulate the current there is a requirement of another to change this basically DC to DC stage. So again we have to there is a requirement to increase the voltage level, and an extra current loop is required to regulate the current. So that is generally known as the fast charging system. If fast charging systems are used, then the charging time can be drastically reduced. So in general, in summarization, the charging infrastructure can be divided into two parts. Either it is a wired system or wireless system. Wireless system is there is a sending end coil and there is a receiving end coil. So there is no electrical connection between sending coil and the receiving coil. And in the wired system, there is a direct connection from the supply to the particular battery. and that can be done through onboard charger if charging infrastructures are not available, and if charging infrastructure are available, then it can be done through offline charger. Now next, another important aspect of the converter requirement is the usability of battery power to the drive. Now, as the name suggests that lead acid battery is the main energy unit of the electric vehicle. Now lithium cell battery voltage is around 48 volt. That voltage cannot be directly connected to the inverter because it cannot drive the AC motor, which generally requires 230 volt system, so AC system. So 48 volt needs to be converted around 310 volt to, or around 380 to 400 volt system, so that voltage, DC voltage, can directly be connected to the inverter to drive the electric vehicle motor, specifically permanent magnet synchronous motor. That's why the high gain boost converters are required. Generally the high gain boost converter, the gain requirement is around greater than 10, or at least minimum is 10, and the duty ratio range should be, operating duty ratio should be 0.4 to 0.7, because conventional boost converter also can be used, but unfortunately the voltage gain is quite minimum. So duty ratio requirement in theoretical aspect, it can be go to 0.8 to 0.9, 0.8 to 0.9, but this duty ratio is not a operational duty ratio for the boost converter or conventional boost converter. So therefore there are a lot of topologies are evolved over the last decade that can give a sufficient amount of voltage gain within this duty ratio range, and having a sufficient amount of efficiency, so the power cannot be power should not be wasted here, that all the power which is coming from the battery should be coming to the inverter. So the this is the, I will discuss in consecutive classes what are the different topologies, why they are important, but essentially this is this operation should be maintained, or at least 10 duty ratio or gain factor, and within the duty ratio range of 0.4 to 0.7. This is what boost converter is, that's why it's required. Another thing is that momentary power, because electric vehicle can accelerate, can be deaccelerated. When it is accelerating in nature, there is a requirement of momentary power or transient power that cannot be supplied by the battery, because battery has very less response time, the main battery unit. So that power can be delivered by a supercapacitor, because supercapacitor is faster in nature. So when there is accelerating power required, the supercapacitor actually give discharging power to the system. And when the electric vehicle is actually deaccelerating, then the stored energy of the wheel can be directly stored in the capacitor. So therefore the high gain bidirectional DC to DC converter is required here. High gain, because the storage unit on supercapacitor, the voltage rating is very less, around 24 to 48 volt, and the DC link voltage is around 380 to 400 volt. That's why high gain boost converter is required for the boosting, for giving the power, and high gain buck stage is also required for charging stage. So that is why bidirectional DC-DC converter should comply these features to charge and discharge the system, or to provide the momentary power, or to store the extra the stored energy power for electric vehicle operation. In the next, there are another section which is the inverter. Now this 300 volt system, 380 to 400 volt system, can directly be converted to the AC system, AC voltage, which is required to drive the either permanent magnet synchronous motor or BLDC motor. That inverter can do this purpose. That is of there are two sections. Either it is two level system. Let me write two level system, or it can be of three level system. If it is a three level system, if it is medium power, if it is medium power and medium power in the range of less than 10 kilowatt, so this is successfully can be operated. In two level, the voltage level either plus or either minus, and in three level it can be 0 and then plus and minus. So this kind of voltage level can be easily achieved for this kind of less rating motor drive, and we do have MOSFETs or not IGBT available for designing this inverter, and it can be successfully operated for high frequency as well. But if the high power rating is used or required, greater than 10 kilowatt or so in that condition the two level and three level converters are not useful. Then we need to use either through SIC converter, because SIC and GN based converter can handle lot of voltage, or it can be used for using multi-level inverter topology. So multi-level inverter topology has lot of switch, low voltage switch cascaded in nature, that can so low rating MOSFETs can be used to block high amount of voltage and can operate in a lesser THD. And that in that condition also there is a requirement of very filter size is also very less. So therefore, in summary, the inverter of two types, either it is a two level or three level type, either medium voltage level or low power level. If it is a high power level, then the SiC and GN is coming in a huge manner. In current technology, as the SiC and GN is not fully proved, so multi-level inverter can also be used to drive for high power rating, where the THD is also less, and we do have can use a lower rating MOSFETs to drive the motor. And another section is the lighting load. As I have already mentioned, different lighting load or speaker load can be managed by multi-port DC to DC buck converter, because it is directly coming from 300 to 400 volt, and that conversion can be done through an isolated converter. So isolated converter means there's a transformer is there, so transformer trans DC we can adjust, and for that we can able to derive 12 volt or 24 volt to run the electric vehicle lighting load or music system load. And finally, the rating of the system. Let us just summarize that already I have mentioned different voltage levels of the electric vehicle. Now let us discuss about the power rating. So for the fast charging, if fast chargings are used to charge the battery, the rating is basically from 50 to 60 kilowatt, and the voltage rating ranges from 480 volt plus. That means it is from 500 to 600 volt system is required. Now, if a single phase or three phase system is used, 230 volt or 400 volt three phase system is used, then the charger rating should be of 7 to 14 kilowatt. And in current generation, based on the battery capacity, there is a how much for a single charge, how much distance one electric vehicle can travel. Based on that, there are different models are available. For Tesla's model, the battery capacity is 10 kilowatt hour. It can go 300 miles per single charge, and if the battery capacity is less, then it can go to 58 miles. For recently developed Nissan Leaf, it actually replaces the battery technology. A new battery technology is being used. It can for 60 kilowatt hour, it can go 300 kilometer for a single charge. So this is about the different power rating and voltage rating. I also have already have mentioned, and all the converter ratings are also there are characteristics I have also mentioned for the electric vehicle. So in the next class, I will be discussing about the requirements, characteristics requirements, and different topological aspects of electric vehicle. Thank you.